Question 2. Suppose that f is Riemann integrable on the closed interval AB. Prove that the absolute value of f is also integrable and that the absolute value of the integral is dominated by the integral of the absolute value. So to do this question, we'll make use of this theorem, and this theorem comes from lecture. It states that a bounded function g is Riemann integrable if and only if for every epsilon greater than 0, there is a partition P such that the upper Riemann sum minus the lower Riemann sum relative to partition P is less than epsilon. So this theorem will be used to solve question 2. Solution. So let's begin by picking an epsilon greater than 0. Then by integrability of f, there exists a partition, the partition of, call it P. We start at A, and we go all the way to, let's say, xj, and xj is B. So we have a partition P such that the upper Riemann sum relative to P minus the lower Riemann sum relative to P, we'll say is less than epsilon over 2, because that's still a positive value. Okay. Then we make the following observation. Observe for all values I from 1 to capital J, there exists an Si and Ti inside here, which is a sub-closed interval relative to the partition. And these have the following properties. There exists Si, Ti such that, first bullet point, the supremum of x of fx, and here I'm going to subtract epsilon over 4, b minus a. This is less than f of si, take the absolute value, and we also have this. Not G, it's F. Okay. Let me rewrite this slightly cleaner for readability. Okay. So how exactly is it that I got this inequality and this inequality? So this is the reason why. So this is the supremum of the absolute value of f, which is the least upper bound. So I took the least upper bound and I'm subtracting a value. Therefore, you are no longer an upper bound. If you are not an upper bound, then some value stands above you. That's what the SI does. On the other hand, the infimum is the greatest lower bound. I take the greatest lower bound, I add a value to it, then you are no longer a lower bound. If you are not a lower bound, then that's to say you stand above some value. That's what the TI allows us to do. So that's how we get these inequalities. It's just by the consequences of ints and sups. So taking this information, and I'm going to cheat a little bit because I don't want to rewrite this. Copy, paste. I have this, And again, I'll have this, but this time I'm going to move this to the other side. So this is going to be moved there, and this is also going to be moved there. So here's what I mean. So that's going to be this plus epsilon 4b minus a, and this is going to be a minus. So then we have these two points. Okay. So because of this, we have the following lines. That's less than this. So epsilon, now I could put a 2. Something subtract its negative. So then we have this line, you see. So then this inequality here is simply because it's simply based off of these two lines here. It's not that controversial. Okay, so now that I have that inequality, I will continue with some fancy algebra work. So from there, I can apply the reverse triangle inequality, which I believe is this. And then I can apply, well, this last one's just common sense if you think about it. The supremum of fx's, subtract the imps of the fx's again, plus this. So then I could go from here all the way to there. And I'll pause and I'll continue in the next video.